Thank you. Hi, everyone. Thanks a lot for having me. So I was asked to give a bit of introduction about ZK proving, and I thought that as a case study, our analysis on proving all Ethereum blocks could be a good introduction to that. So before we go into the details, just a quick recap of what ZK is. I mean, yesterday, Sergey at this very stage gave actually a pretty good intro, so I'm not gonna go too deep in there. His talk was excellent. So it's, in a nutshell, ZK, a cryptographic primitive that allows one party, the prover, to prove some knowledge of data to another party, the verifier, without showing the data itself. And like, it allows the verification of the correctness of the data, but also also the correctness of computation over that data. Some of the main use cases of ZK, as you most probably know, are privacy and scalability, and obviously others as well. But like, when we talk about privacy, we talk about any use case that has anything to do with sensitive data. It could be finance, identity, healthcare, etc. And based on the definition, we could say that you are, with ZK proofs, you are able to prove that you are over 18 without revealing your date of birth, for example. Now, in this case, when we talk about privacy, the privacy aspect of ZK, proving takes place on the client side, which means the client device, the mobile phone or the browser, has to generate the proof itself, or else the sensitive data would be exposed to whoever is generating the proof. Now, the opposite is scalability, or how ZK is used on the scalability side. A good example is ZK rollups, where usually the workloads are much heavier, and therefore you require a cluster or multiple clusters of powerful hardware to generate the proofs for entire batches of transactions or batches of blocks. And due to this, these types of proofs are usually generated on the server side, as we call it. So in general, traditional blockchains have been re-execution based. For example, Ethereum, there is a proposer for the next block, they build a block, they propagate it through the network, and every other validator has to re-execute that block to come and see whether they come to the same results, the new state, basically, to verify the correctness of the execution, the correctness of the block. And because of this, if you imagine, there is tons of redundant, or we could say wasted compute, but you know, this wasted compute is part of the security. However, with ZK proofs, there could be a proposer who builds a block, executes it, and then sources a proof from some source on the correct execution, and then the rest of the validators wouldn't need to do the re-execution, but just verify a very succinct proof on the correctness, proving the correctness of all the state transitions, etc., included in the block. And the reason why it's important is because, imagine there is only a very small succinct proof, few hundred kilobytes, and a very like a device with negligible hardware resources that could actually do the verification. It could even be done in browser, to be honest. Before we go into details, a quick recap on what we do. I work at ZkCloud. We've been building the first universal proving infrastructure, and we've been working closely with teams like the Ethereum Foundation, the Aztec Network, and many other roll-up teams. And we received a grant from the EF to prove every Ethereum mainnet block in Q2. That's how we landed up with this challenge, and also to make optimizations wherever we can to the proving process. Now, let's go to the case study itself. I think there was a talk yesterday by Justin Drake, who was mentioning the ETH Proofs initiative. It's been launched by the Ethereum Foundation in January this year, if I'm not mistaken. It's a public platform to track the performance of ZK VMs, proving services, and to facilitate the race to real-time proving of Ethereum mainnet execution. We joined in March 2025 and started proving every Ethereum block as of the 1st of April. posting every block to the staging interface. So if you go to the staging interface, actually it's public, so you can even go there now. You can find all the proofs uploaded there since the 1st of March in case you need it. And then the production interface of ETH proofs is actually showing proofs generated for 1 out of every 100 blocks. So we are posting it there to the production interface. Now, why is proving Ethereum important? I'm pretty sure you've seen a lot of discussions around these or blog posts and communication around these. Ethereum is going ZK. It seems it's not a question anymore, even though it's going to take some time. But the reason why we wanted to participate and contribute to proving Ethereum's execution, even at this point, is because we wanted to prove that, proving the entire execution has been viewed as prohibitively expensive and infeasible, and we just wanted to prove the opposite as a project building prover infrastructure. The ZK endgame is here today. It's affordable even today. You'll see some figures in my upcoming slides, and we wanted to demonstrate this economic feasibility. Our roadmap was simple. We started off with single GPU proving. That's how also the ETH Proofs initiative started. We recently moved to multi-GPU proving, and then obviously our goal is to get to real-time proving. We are not quite there yet, but getting there quite fast, I hope. And the reason why real-time proving and ZK is important for Ethereum from the L1's perspective, I just included a tweet from Justin, an earlier tweet from Justin. You can scale the throughput of Ethereum mainnet by 1000x if you switch from re-execution to snark verification. And then on top of this, obviously, could be added all the additional throughput processed through the L2s, as he mentioned also in his talk yesterday. A few details about single GPU proving. For this, we've been using a cluster of 24 4090s. With 24 4090s, one GPU thrown at every block, we were able to keep up with the chain, and we even had a bit of redundancy. We were using SP1, Succinct's ZKVM, and we used also a modified version of their block prover, RSP. I'll talk about the modifications we've done, or some of the modifications that we've done. We generated over 1 million proofs. It's basically, so with a 12-second slot time, Ethereum has approximately 200,000 proofs a month, 200,000 blocks a month. And if you multiply it for about 5.5 months we are now since the 1st of April, that's how we are at this number. The average proving time with a single GPU is, with a single 4090 is around 3.5 minutes. Even though I have to say this is somewhat, this used to be somewhat smaller, around 2 minutes and 50 seconds, but there has been an increase in the gas limit from 36 million to 45, and you can see it, see the increase in the average gas usage in the blocks as well. The average cost per block is literally slightly over 2 cents. And if you imagine there is 150, 200 transactions on average in a block, this lands with, sorry to say this, but like Solana type of negligible transaction fees, like 100th of a cent, basically, which is why I said actually ZK proving, if we were to add this cost to the transaction fees of Ethereum, you wouldn't notice it, basically, even now. The proving phase, the proving process actually consists of 2 main phases. So there is a pre-proving phase and the proving one. Interestingly, the pre-proving phase even used to take longer than the actual proving in many cases, and the reason for that is that the pre-proving phase includes fetching of all the input data through through RPC to reconstruct the block itself, and it took something around 4,000 to 5,000 RPC calls, mainly ETHGET storage at ETHGET proof and some others, to reconstruct the block itself. It accounts to over 1 billion calls per month. This is very, like, the back and forth of all these calls used to take several minutes, even for an average block. And because of that, it was really a headache. So we've been, one of our engineers has been heads down for 6 to 8 weeks to implement a custom fetcher, which is using Reth's custom method, which is called debug execution witness. And this can fetch all the input data in a single call. I think some teams, for example, Scroll, implemented this in their latest client by default already, but Ethereum clients haven't used it by default yet. However, implementing a new method meant that we also had to re-implement how the Ethereum prover binary actually builds the MPT from the execution witness. So that was the main chunk of the work. But with this, from hundreds of seconds, we were able to go down to somewhere around 0.5 seconds for like super large blocks. It's closer to 1 second, but it's been a huge improvement. If you check the screenshot here, you can see that we are not the fastest in the proving time on this screenshot. On the other hand, we are way faster than everybody else on the total time to deliver a proof. And the reason for that is because everybody else spends 5, 7, 6 minutes. I think even Succinct, who is the fastest in proving, spends almost 2 minutes on the pre-proving phase. This is what we've reached with debug execution witness.
Could this be improved if you locally run a node and the RPC calls just...
Actually,
why is this not, let's say, the first approach to the solution?
yeah, the thing is that we've tried very many approaches. Even like we have our own Ethereum mainnet archive node running in on the same bare metal cluster where we have and it still took a few minutes. It was just too cumbersome. We tested most of the RPC providers, GCPs, every different setups. And finally, the fastest one obviously was using our own archive node. But it just didn't help us. We had to go with the archive node because if there was some issue with proving of previous blocks, that way we could actually replace them and generate the proofs for older blocks as well. And the funny thing is that a few days later, actually it was around 2 weeks, Succinct Labs also took our implementation, which was open sourced through a pull request to the Reth repo, and they pulled it into RSP. So they are already supporting this since late July as well.
Sorry, one question.
Yes.
What is the pre-proving phase looking like? I guess collecting data, or?
It's mainly fetching inputs and doing some massage over the data to feed it into the ZkVM. And then actually when you call prove within the ZkVM, it includes the trace generation, that part. So the proving phase includes the trace generation as well, plus the actual proof generation. So it's more like fetching and preparing the inputs for the ZkVM.
Okay, and that's the kind of the bottleneck, let's say, for this process to be way faster.
One of the bottlenecks. So for the pre-proving phase, yes, this was our main bottleneck. In the proving phase, there are two things. I may be getting there, but there are two things. Generating the witness takes somewhere around 10 to 20 seconds, even for an average block. For example, with RISC-0, it's around 10 seconds. With SP1, it was somewhere around 10-15. But ZkCloud, I don't know if you know the ZkCloud team, they have reached amazing results in generating the trace, something like 1.5 gigahertz, so almost native performance in generating the trace. And that's the next bottleneck, because the trace generation does not, by default, it doesn't use GPUs yet. And it's a sequential process, basically, that you cannot parallelize. At the very end of the presentation, I'll talk about a method that SP1 developed. It's called sub-blocks. And we are also exploring that to make parallel processing of trace generation to implement that process in trace generation as well. I'll get there, and I think there will be some more details there. So as you see, the pre-proving phase doesn't require GPUs, very minimal, few threads, 4 gigs of RAM on average. However, the proving phase requires about, on average, about 22 threads or virtual cores, with the maximum we have observed 42 cores and an average RAM of almost 40 gigs. The maximum we've observed is 65. And interestingly, even though the 4090 has 24 gigs of RAM, the proving process only utilizes around 16, so there is quite some optimization still to be done on that front, so that we could actually utilize the additional 8 for example, for aggregating smaller, for the aggregation part of the proving process. Some of the modifications that we have done, the first one was to decouple the pre-proving phase from the proving phase, because the prover trait in SP1 has been built in a way that the SP1 prover, which does not use GPUs yet, and the SP1 CUDA prover, they were coupled. So whenever you initiate the process, the GPU is already logged in, even though it's not being used at first. So this resulted in a lower GPU utilization. So by decoupling these two phases, we were able to do preparation for certain blocks parallel to the proving of other blocks and increase GPU utilization. And also, the proving flow in SP1 consists of these commands: setup, execute, and prove. And setup actually is responsible only for generating the prover key. It doesn't modify any internal prover state. So, and we found it's possible to generate the prover key and then reuse it, generate it once for a given client binary and then just reuse it. So we can just skip it and save 1 or 2 seconds. And then we also skipped calling execute, because execute was there only to add the cycle count to get the cycle count. So what we did is we made sure that the proof call includes exposing the cycle count, the total RISC-V cycle count for the proving job. And funny enough, we were obviously having our fork of RSP, and the succinct team turns out watching forks actively, because we implemented this and the next day they implemented it too. So they were really actively watching the forks and what's happening on the forks. It was pretty cool to see that we are basically helping each other this way. Yes, and then if we go to multi-GPU proving, the reason why we use RISC-Zero's latest VM for multi-GPU is, one of the reasons is because SP1's multi-GPU orchestrator is not open source. While RISC-Zero has both the ZkVM and the multi-GPU orchestrator called Bento open sourced. Also ZISC and I think Airbender has both of them. We are in the process of testing them as well. But RISC-Zero seemed to be the most natural fit for us first. The process is the same. We use debug execution witness for pre-proving, and then the proving phase includes execution and proving itself. We use a cluster of 48 4090s for this, and we currently have an average proving time of around 30-35 seconds. We are still approximately 2.5x away from the 12-second real-time proving thing. However, one of the main bottlenecks that we are having is that if you see the cycle count compared to ZISC here, it's almost double in RISC-Zero, and the reason for that is that there is an issue with signer recovery. So Ethereum transactions don't explicitly store the sender address, but instead the ECDSA signature over the payload. And to validate the transaction, this sender address must be recovered from the signature. This is signer recovery, and even though there is a precompile for ECDSA recovery, it's still counted in as cycles and it's still being executed that way. So unfortunately, it doubles almost our cycle count, which would result in somewhere around 16-18 seconds of proving time total. So we are working heavily on that. We opened an issue to risk zero as well. And actually, it seems I'm talking much slower than when I was, rehearsing at home. So I'll try to speed up. Some analysis of blocks. So 11 million, these are all blocks around 11 million gas from a close range. So this is an everyday block building flow. And you can see that even though most of them translate to around 200 million RISC-V cycles, third column, and around 2-minute proving time, even in an average block building flow, there are some significant outliers. One with 280 million RISC-V cycles, one with 320. And you see that this is almost 3 minutes, that one is 3.5 to prove in comparison to the others. The plotted chart shows that there is basically a moderate negative correlation between gas usage and RISC-V cycles. And I'm going to talk about the reason for this. If we look at divergence from mean, then we can see that the gas usage varies by 16% among the blocks that are analyzed here, while the proving time varies by 80%, which is quite a lot. On the other hand, the cycle count versus proving time, there is a very strong correlation there. So the higher the number of cycles, the longer the proving time, we could say in simple terms. This is an extreme example, a block around 24 million gas. And I took, on the plotted chart, you see other blocks which are around 20, 21, 22 million gas. And most of them fall in the 400, 500 million cycle range, while this one is over 1 billion cycles. And the reason for this type of asymmetry is that there is the proving complexity of different operations is very different. Basically, there are some precompile operations like modXP, which is 200 gas, but it translates to almost 220,000 RISC-V cycles. So there is 1,000x there. BN pairings, there is almost 40x overhead there. Operations with memory access and copying are also expensive to prove. A simple jump test, one gas, it's also like 1,000x overhead. So this is a potential attack vector. What if a proposer would on purpose build a block which is impossible to be proven in real time? Even if, like, once Ethereum goes full ZK and consensus and execution is based on ZK, then it's a potential attack vector. And all this data can be found in actually Connor's repo, ZK Carnage repo. It's very good. He did a bunch of analysis around this, and he's also been building so-called prover killers, on purpose building blocks that are testing ZK VMs and proof provider performance to see how they act with such proof-heavy blocks. And what's next for us, this is basically my last slide, RSP sub-blocks. The main difference how segments or shards are used in RISC-0 and SP1 is that RISC-0 and SP1 earlier, they executed the block in the ZK VM, generated the block, the witness, and then split it into segments, proved these segments, and then aggregated them. However, what SP1 figured out is you could execute the large block outside the ZK VM, then collect so-called sub-blocks, mini-blocks, and execute them in parallel within the ZK VM, prove those sub-blocks, and actually execution of sub-blocks in the ZK VM means you can generate the trace for them in parallel as well, instead of like a big sequential trace generation process, and then aggregate the proofs of those sub-blocks. This is super cool. We are heavily investigating this and implementing it in our prover. And just a last slide to recap. Why is real-time proving important? It's a 1,000x increase in throughput for Ethereum. And if we look at the L2 landscape as well, like real-time proving would unlock deposits and withdrawals between L1, L2, L2, L2 in one block, bridging between rollups in one block, composability, etc., etc. So there is going to be a huge UX increase and like I'd say fragmentation, the current fragmentation of L2s and in the Ethereum ecosystem would actually disappear with the implementation of this. Thank you very much. Unfortunately, I ran out of time, so I don't know if we still have time for some questions. Not really, but I'm happy to take any questions like offline.